Okay, so the next step in what we do here is trying to imagine how things are going to be done three-dimensionally. Three-dimensionally. Because, I mean, the whole point of today's lecture is to discuss a very classic and simple, and I'm going to use the word simple in the most grotesque way I could, but one of the most simple problems that is a practical problem that we have in quantum mechanics is the hydrogen atom. Now, it's by no means simple, but in reference to all the other problems we could possibly do, it actually is simple. But it does involve us invoking three-dimensional things. So now, the first thing we want to do is look at the particle in a box problem that we had done earlier, but apply it to three dimensions. That's the idea. And so I'm going to write at the bottom here the following. For a particle, free particle, that means no potential here, the kinetic energy of this particle is going to be equal to so that's the x dimension stuff. We're going to write the kinetic energy in terms of the momentum. So the momentum obviously is m squared v squared. That's equal to 1/2 mv squared. But this is three-dimensional. So there is a term for every dimension. And recall that for any given dimension, which I'll just label to be sort of S here, that we have the Planck constant over 2 pi times a value for k, but that k is going to have a subscript, that's the wave number, for that particular direction. And of course, we know from previous stuff that h bar squared ks squared over 2m is going to equal h bar over omega, and I'll put a little subscript on there as well, s. That's all the stuff we had before. So now the fact that we have three terms here means very likely that we have three terms in the Schrodinger equation. And that's true. And that's really the only variation we have here, is that having three terms for kinetic energy, because that's how we identified this first term here. This first term is a statement of kinetic energy. And so having three terms, well, we're just identifying the three dimensions that you can have kinetic energy. Of course, potential energy remains the same. And if we are dealing with the time-dependent equation, the right side still looks like I h bar d psi dt. And that is, this equation here is just sort of generally what the Schrodinger equation looks like in rectangular coordinates, okay, and time-dependent. Now, if we want to talk about a time-independent equation, well, what we're going to do is this. We're going to have our capital psi, which is going to be x, y, z, and t, and we're going to relate that to a lowercase psi, x, y, z, and the time component is going to be the same stuff that we had developed previously, which is I E T over H bar. And that's really not going to be any different. So we can take our time-dependent equation, make this substitution. We will divide out all of the exponentials here, and the right-hand side will turn into just energy. And then we are left with a familiar time-independent Schrodinger equation. It looks completely identical to what we had before, except there's three terms here. three partial derivatives for the three dimensions we're going to work with here. Now, one thing that we can do here to simplify things is having the second partial derivative with respect to x, y, and z. This whole thing collectively has a formalism in mathematics, and that is called, what is that called? There's a name for it. Shoot, what did I do with it? What did I do with that name? Give me a second here. I thought I wrote the name down. Oh, brother. Second. Can't believe I didn't write the name down.
Is it like a special partial derivative or something?
Yeah, but there's a special operator called the... Shoot. Not that one. My goodness, I can't believe I forgot this. Killing me. Ah, the Laplacian. I'm such a dummy. Sorry. All right, this is called the Laplacian. Why didn't I have that? Laplacian operator. Yes. Oh, all right. So anyway, this entire expression here can be written as the following. Where's my marker here? So this is a del symbol squared times the wave function. And this operator is understood to be the partial derivative of x, y, and z added together. It's called the Laplacian, which is a good Scrabble word, if you're so inclined in that way. I did a lot of Scrabble over the Thanksgiving break. That was how I occupied my time for the most part. Love Scrabble. Anyway, it's called Laplacian, and it has many forms. In the Cartesian rectangular coordinate system, it's this expression I outlined here. Okay. It will have a different form if we choose a different coordinate system. You will see that a little bit later. Let's move on. All right, so we're going to go back and consider our particle in a box problem. We did a one-dimensional particle in a box. And one of the things that we'd like to consider is the particle in a three-dimensional box any different? Well, it's a little different, actually. It's a little different. So in the particle in a box problem, just to be super clear, it's a free particle, so that our potential energy function is 0. We don't have that term in there. And so in order to solve this equation, so if you go back and we think about Schrodinger's equation here, this term at the bottom with u is 0, right? So we need to figure out solutions to the equation if this term is 0. And we're going to make an assumption, which turns out to be correct. But, and if you've taken, what's diffie q? Is that 250? No, it's 240, right? Is diffie q 240?
230, I think.
230. Oh, brother. 250 must be multivariable, and then... Oh, wait, what's linear? Is linear 250? I don't know the numbers.
Linear's 220, yeah.
Oh, brother. Okay. Oh, there's no 240. Okay, anyway, I'm not taking classes, but I know that there's these 3 higher level things. Anyway, it's diffie q for those who have. One common method to solve equations is something called the separation of variables. So our wave function in x, y, and z, we are going to make an assumption. And it's a fair assumption. We do believe, it's not wild to think this, but the wave function should be able to be broken into pieces that are completely independent from other dimensions. So here's what I mean by that. Our wave function, we're going to assume, takes this form. Capital X of x, capital Y of Y, this is an X here, capital Z of Z. So we're going to make the assumption that our wave function for the three-dimensional free particle problem can be specified by three independent spatial functions, X, Y, and Z. It's not a wild, it's not a terribly wild idea. It is anticipated, and it does yield some nice solutions, so we're going to go with that. So if we go back to this equation here, plug in the separation of variables, okay, and then divide by this equation, we're going to get the following stuff. I'll just show you the first term. So we get our h minus h bar squared over 2m, and we're going to have our wave function in terms of x times our second partial. Well, I'm putting it as a partial, but it's not a partial anymore because we broke up our function. Because when I divide by the wave function, the y's and the z's drop out. So this is not technically a partial anymore. I mean, I guess I'll try to write it as a dx over dx. And then we'll have another one. This is the minus sign, actually. H bar 2m 1 over y d squared y over dy. And so on. That's going to be the equation. Of course, that's going to equal E, because we divided by the wave function. So the wave function on that side of the equation is gone. So those are our terms there. And of course, the energy, the overall energy, this term right here, is going to be EX, EY, EZ. And that equals Z. So what we have here basically are three independent equations that involve the second derivative equaling the respective energy in its dimension. So what's my next slide here? Well, I'm not there yet. So let me just show you one. Here's the x direction one. And by the way, when I show you the x direction one, you can apply the same stuff to y and z. So the x direction one is going to look like this. Minus 2h bar over 2m. So this is going to be the second derivative of x. And that's going to equal e sub x times, well, times their function in x. So this equation appears three times. X, y, z. This equation, however, has a very nice solution to it. It's the second derivative equals the same function times a constant, which is just sine and cosines. So ultimately, when we go through this, we find that the solution in one dimension is really no different than the solution in two dimensions. So I'm going to bring up a screen share here so I can just complete this. If I solve purely for the derivative, d squared x of x dx squared, and that's going to equal minus 2me h bar squared x dx. There's an equation for y and an equation for z that looks completely identical. The solution to this particular equation has a very nice solution to it. It is, in its most complete form, a cosine radical 2me over h bar x plus b sine radical 2me over h bar with an x. And then there's an equation, there's a y that looks completely identical, and a z that looks completely identical. And those are the solutions. Now, for all of these, we have our boundary condition still. That in the box, at 0, the wave functions need to be 0. So that would apply for y and apply for z. And what that means is a is 0 for all the cases. You need to have A0 in order for the wave functions to be 0, because normally cosine is, 1 at 0. And then we have the condition that at L, which is the dimensions of the box, we need to be at 0. But when we do that, all we have is B left. Well, there are some nice solutions there, because what happens is we end up having this expression right here. B sine, this is going to be what? Radical 2me over h bar L equals 0. Well, again, just like we had for our particle in a box problem here, that means that this argument here, the radical 2me over h bar L, is got to equal multiples of n. And that, again, is true of every single dimension here, x, y, z. When we pull all of this information together, we end up with the following expression here. We end up with the wave function being the product of 3 sine functions, x, y, z. I've kind of grouped all of the possible coefficients together into a single one that I'm going to call C, because remember there was like a B for x and a B for y and a B for z, but I'm going to combine all those to a single constant, which I'm going to call C here. Now notice there are 3 quantum numbers here, x, y, z. So the energy that a particle can have can be distributed across these 3 dimensions, which, by the way, not surprising. If you remember way back at the beginning of stuff here, this is how we treated the things in thermodynamics. That there are degrees of freedom, energy states in different directions, so this is not a surprise here. This is still the same. If we want to figure out what C is, again, we do the same thing where we want to do a normalization. You want to integrate this. We want to square the function. That's the probability function. And we integrate it over the space of the box and set equal to 1. I guess I worked that out later. Okay, anyway. So this is how we'll get our normalization concept. We'll worry about that later for now. But we have to square this equation, integrate over the length of the box, is that equal to 1, solve for C. We'll get to that in a minute here. These are some solutions, different quantum numbers for nx, ny, and z. So for this particular solution on the far left here, the quantum number for x is 2, and then 1 for y and 1 for z. And what that does, it creates a box, but it creates 2 distributions in the x direction. And in the middle, everything's 0, and we have the highest probability in the x direction to be in the middle of these 2 little slabs here. You can do the same thing for y and the same thing for z. All this stuff is the same. It's just a matter of how we break this box up into smaller boxes. And so if we half x, half y, or half z, our particle is more likely to be, in the middle of these boxes. So that's the idea. Okay, so a couple questions first, and we'll keep going with this. The particle's in a cubical box with sides at, well, it's just a standard cubical box with sides L. When the particle is in the state 2, 1, 1, what positions is there a 0 probability of finding the particle? So, give me a letter, what do you think about that? So, the quantum numbers are 2, 1, 1, which is the situation on the far left here. All right, everybody's saying A. A is good. Yep. If the quantum number for x is 2, then you have 2 regions, and in the middle it's 0. So that's good. Okay. So let's do a couple problems here. I got my slides for this. Find the normalization constant for the 3D particle in a box. Find that probability that the particle will be found somewhere in the region of 0 to L over 2 for the cases of the following. All right, so first thing first is find the normalization constant. That requires us to do a triple integral over x, y, and z. We're going to square our wave function, which I've done right here. Now, the wave function does separate by variables, so while it's a triple integral, it's really not a triple integral. The c squared is going to lay in the front here, and we have our sine function squared in x, y, and z. Due to the separation of variables, it's not really a triple integral. Now, in order to integrate the sine squared function, I'm going to make a substitution like we've done previously when we did the particle in a box problem, that sine squared is equal to 1/2 1 minus cosine 2 theta. Now, I left out my angle here. This should say sine squared theta, and I forgot it. Don't do that. That's a bad thing to do. And we're going to plug that in to each one of these integrals here. So I'm just going to do the one for x because the other ones work identically the same. So I plug this one in for x. I get the 1/2 1 minus cosine. I put in what well, no, that's the same stuff there. And we integrate this, I get x over 2 minus L for nx pi. That comes from the integration here. This turns into a sine function, and I evaluate this from 0 to L. Well, 0 is not very interesting because everything comes out to be 0. And I plug in L here. The sine function turns to 0, and the whole thing just turns into L over 2. So I do the same for y. I do the same for z. And each integral gives me a factor of L over 2. So the equation becomes c squared L over 2 times L over 2 times L over 2. Solve for c. We get 2 over L, 3/2 power. That is the normalization coefficient. So now with this factor in the front of this, when you integrate this function over the box, you get a value of 1, which is what is required in normalization. Now, I just want to figure out the probability. All right? So if I want to figure out the probability for 0 to L over 4 for the following cases, what I got to do is I got to do the same thing. I square my wave function, and I integrate over the regions of interest. Now for x, I'm integrating from 0 to L over 4. For y and z, it's still the same limits, 0 to L, 0 to L. Because I'm just exploring 0 to L over 4 for x. But it does require you to look over all of the y and z coordinates. All right, so if I do that here, I already know what the integrals are going to be for L and Z. Sorry, not L and Z, Y and Z. That's L over 2. That came from the earlier stuff here. And if I integrate from 0 to L over 4, I get a different expression in here. So I have my constant out in the front. It's cubed 2 over L. It's cubed now because we already squared our wave function. That's why the over 2 is not there anymore. We got 2 factors of L over 2 here. And then here, I just plugged in L over 4. So we get L over 8 here, and then this is, minus L for nx pi. And over here, it's going to look a little different, obviously. It's going to be L over 4 here. So I get a pi over 2 nx. And this then simplifies a lot, actually. This bracket here simplifies to this. When I multiply by the normalization constant and the L over 2 squared, I end up with this thing here for my probability. So just to be clear, we did the exact same procedure we did before to get normalization constant, except we did one thing different. We changed our x limits of integration. And now we have this function here, which tells us the probability for given quantum numbers. Now, the quantum numbers for x and y don't matter here. This is only interested in quantum numbers for x. The y and z don't matter. So we see here that we have a quantum number for x that's 1, 2, and 3. The fact that the other quantum numbers may be different doesn't play into this at all. So I simply plug in to this equation here, quantum number 1, 2, and 3. And we find that for quantum number 1, we don't have a huge probability, about 10%, which makes a lot of sense. It's actually not 10%. It's more like what's closer to 11%. I mean, it's not 11%, but the idea is that if we force the particle to be in quantum number 1 and different quantum numbers for y and z, we break up the probability of the different dimensions there. It turns out to be just about 10%. For quantum number 2, 25%, and quantum number 3 is 30%. So it actually increases as we get the higher quantum numbers. And in the way you can visualize this is you go back to this figure here, and you just imagine this picture. My mouse has disappeared. But this picture looks different corresponding to the quantum numbers. So like a 311, right? 311 would be like this picture on the left here, which is 3 divisions in the x direction. So with 3 divisions in the x direction, there's a pretty good probability, at least a third probability, that you're going to be in the far left one. So that's why that probability comes up to be 0.3. So, all right. A lot of math there. I mean, this whole thing's a lot of math, you know. So let's keep going with it, though. All right, let's see here. How are we doing on time? Shoot. Well, I'll do a couple more slides, then we'll break and do our hydrogen atom. So when you want to evaluate the energy of these things, the energy is going to look very familiar. The only change is that we have contributions in x, y, and z. So this formula is the formula we developed before for the one-dimensional particle in a box. The only difference is now we have dimensions in y and z. So now this quantum number term here is x squared, well, nx squared and y squared and z squared. And so that's how we represent the energy for the three-dimensional box. We consider each dimension. Now, because of this, there are many combinations of integers that will result in the same energy. And we call that, in physics, degeneracy. Degeneracy is when you have different states of a system resulted in the same energy. So if we look at this graph here, for example, having quantum number 111 results in a particular energy level. And there's one unique state of that energy level. But quantum number for x being 2 or y being 2 or z being 2 results in the exact same amount of energy. Nothing's really different there because if you add up a bunch of ones that are squared, you get a 3. Okay, if you add up 2 squared plus 1 squared plus 1 squared, you get a 6. So that's exactly double the amount of energy. But there are 3 states that give that. So there is a degeneracy in the state. There are 3 degenerate states that result in this. If you have 2 of your dimensions be quantum number 2, that results in degeneracy again, because you can pair up any 2 dimensions, x and y, x and z, or z and y. And that results in 3 times the amount of energy. There are 3 energy states that work for this level, 1 here, and then the top one here has 6 states that result in the same energy difference. So when you go back to this statement here, nx squared, ny squared, and z squared, there's a lot of combinations that result in the same energy. So there are multiple degenerate states here.
So, I guess, I mean, I don't know if this is like observed from the graph you showed, but are there only like non-degenerate states when all three of the, like each x, y, and z state is the same? Like 1, 1, 1, and 2, 2, 2? Or is that the only case where it's unique?
Well, I'm not positive because that basically, the question you're asking turns into this. Are the sum of the squares of integers equal to the sum of squares of other non-unique integers? I don't know the answer to that question. For example, if you go high enough, is 4 squared plus 4 squared plus 4 squared possibly equal to like 6 squared plus 5 squared plus 1 squared? I don't know that. My guess would be they would be some combinations of integers where they are equal. And if that's the case, it's not unique then.
Okay.
Honestly, off the top of my head, I can't think of an example. But again, these are not easy numbers to think about. But yeah, I mean, basically, is the sum of the squares of a set of integers equal to another sum of a square of set of integers? Probably. Off the top of my head, I can't think of anything. But I'll let you know if I do. Because we're going to take a break in a minute. And guess how I'm going to spend my break now? I'm just going to find integers that satisfy this. And I bet you anything I can find a bunch. So I'll let you know in about 10 minutes.
All right, for sure. I just thought.
No, it's true though. There's a pattern here, right? But the idea is this: you got to go and you got to look at this part right here. It's this part right here, the nx squared plus ny squared plus nc squared. If you can cook up integers to equal a certain number, and then you have another set of integers that come up with the same number, well, there would be degeneracy there. So that's the idea. Anyway, so that's what I'm going to do for the next 10 minutes. We're going to take a break, 10-minute break. We're going to come back, and then we're going to take the ideas we developed here, and we're going to tackle the hydrogen atom. This is going to be fun, but extremely frightening. I'll just tell you that. The solution to hydrogen atom is completely insane, but we're going to have fun. So I did look up, is the sum of 3 integers equal to the sum of another 3 integers? And apparently the answer is yes, and the number of solutions are infinite. However, I could not dig up a single example, but this is called a Diophantine equation. Diophantine equation. And I could not. So Diophantine equations are apparently sums of powers. So it's more than just squares, but apparently there's an infinite number. But I'm a little disappointed that I couldn't even come up with one. We had one worked out example. Maybe it's because it's not simple. Anyway. What the hell? Oh yeah, that's weird. All right. So, okay. Let's get to the rest of this. Strap in, people. Buckle up. It's going to get wild. All right. So, we are now going to try to take the principles we've developed so far and apply them to the hydrogen atom. Hydrogen atom is obviously the simplest atom we can work with. It has a single electron and a single proton in its nucleus. And so it's not a free particle. It has a clearly defined potential energy state, which is given by the potential energy of 2 charges, which you'll see in a minute here. And just like the 3 dimensions for the particle in a box, there are going to be 3 dimensions for the hydrogen atom and 3 quantum numbers. But we are not going to do this in X, Y, and Z because there's a lot of spherical symmetry in the hydrogen atom, and that's actually going to require us to switch over to a different coordinate system. Instead of a rectangular coordinate system, we're going to work with a spherical coordinate system. So instead of X, Y, Z, we're going to work with R, theta, and phi. R is a distance from the center. Theta is an angle made with respect to the z-axis, and phi is an angle made with respect to the x-axis. And so these 3 coordinates, r, theta, and phi, do represent a unique set of coordinates that are independent from each other and can be mapped to x, y, and z. And so that's how we're going to solve this problem. It is a complete monster of a problem. In the spherical coordinate system and in the rectangular coordinate system, it's even more of a nightmare. So switching our coordinate system makes things a bit nicer. The R function has quantum number n, which is the stuff that you are familiar with already and is just sort of dictating different energies. The theta function has quantum number that we're going to describe as L, which has to do with the angular momentum of the particle. And phi has a quantum number that we're going to label as M sub L, which is the z component of the angular momentum. So let's jump into it. This is our equation up here in rectangular coordinates, which again, we don't really want to do. The Laplacian in Cartesian coordinates is given by this statement right here, which is the partials in x, y, and z. In spherical coordinates, the Laplacian has a completely different form. It takes the form of a nightmare, which is given right here. So instead of these 3 partial derivatives, we have these other 3 partial derivatives. 1 over r squared, partial with respect to r, times r squared partial with respect to r, is 1 for theta, is 1 for phi. Okay, as you can probably tell, this is not the most exciting stuff that we could do. This is the kind of stuff that, well, will take many hours of your day. Which, yeah, it's a monster. This is an absolutely insane operator. The first term here does exclusively work on r, but then when you move to the second term, we have r in addition to a bunch of other things that involve theta, and then the phi component over here has both r and theta in it. So this is pretty wild, and as you can probably tell, we are not going to make an attempt to solve this thing. Not at all. In Schrodinger's equation, however, the potential energy function is rather simple. It does not contain any theta or phi components. It's purely r-based. This is the value for the potential energy function. It's E squared, 2 pi epsilon naught over r. Again, this is, if you've had physics 120, you've seen Coulomb's law and the potential energy function that goes with it. If you have not been to 120, don't sweat it. I'm just going to state this for you, what the potential energy function is. Let me bring up a screen share here to try to communicate to you some of the stuff we're going to work with here. Where's my... There we go. So we are going to do a similar idea where we assume that our wave function can be broken up into independent variables. So this is, the wave function is going to be in terms of r, theta, and phi. And we're going to imagine that is going to be broken up into a separation of variables that is going to be capital R of R, capital theta of theta, and capital phi of phi. So this is what we call the separation of variables. And there is an assumption here. The assumption is that the other variables don't really influence each other, which happens to be true, actually. So the radial component, when you plug everything in and you attempt to clean things up, the radial component of the wave function looks like the following here. So you get your minus h bar squared over 2m. But then we got to put in the Laplacian stuff here, which is divide by r squared, dr, r squared, dr, plus, I'm going to have an h bar squared over 2m r squared. This is a little r here, and I'll explain this in a moment. These are the quantum numbers in the theta component. So that's what the radial component of Schrödinger's equation looks like. The angular part of this, meaning the theta part, looks like 1 over sine theta d theta of sine theta. That's capital theta of theta over theta. Plus, again, we have our quantum numbers here. Actually, that's not there at all. Take that out. So don't panic too much here. I'm not going to require you to work out this stuff. This is insanely complicated mathematics here. This is another quantum number. And then the last part is the phi component, which is the phi component actually has a very nice solution to it. This is phi equals 0. Right, so this is all pretty, I mean, these are insane functions. We don't have any hope of solving any of these things, to be honest. But I will show you this. So let me bring up a web page here. Where is that web page? Is it here? Oh, I did I close it out? Give me a second here. I accidentally closed it out. Discard. Let me bring it back up. Where is it? That's weird. Oh, here it is. So, if you take those three equations and you attempt to solve them for their respective terms here. So here's what the Schrödinger equation is. When you separate the radial part from the angular part. Let's scroll down a bit though. When you solve the individual pieces, you get this down here. Let me bring this up. So this is the radial component, angular component, the phi component. It's going to be n is just part of the normalization constant. The radial function, the angular function, and then e to the im phi represents the z component function, where Rn is a series of complicated exponentials, which take this form here. Again, I don't expect any of you to really follow much of this. I'm not testing you any of this stuff, but I'm just sort of exposing you to what you could deal with. The p values, which are part of the angular part, are what are called Legendre polynomials. Which, where are those? They're here. This entire insane expression here are the Legendre polynomials. So I'm going to try to simplify this as much as possible, but the solutions to the stuff end up being pretty wild. When you solve the R component to this, though, the R component does yield, when you eventually get through all the mathematics there, a somewhat simplified energy state equation. Now, you've seen this before, actually. Let me get out of this. Wait, what's my mouse? Hold on. My computer is freaking out on me. Uh-oh. Okay, I think I figured it out. Okay. So, in terms of the energy states with respect to R, okay, we end up with this expression here, which you've seen before, by the way. The 13.6 eV over n squared, that's what the Bohr model predicted as well. So it's pretty much identical to what quantum mechanics has to say. Actually, when I say pretty much identical, it is identical. But of course, the quantum mechanical treatment comes up with a lot more than can be done with the Bohr model. So we have n, which represents our principal quantum number. So what I want you to think about now is this. Think about the periodic table. Okay. The first row of the periodic table are the n values. Okay, the n values. So n equals 1 is the first row. Hydrogen, helium. N equals 2 would correspond to the elements below that. So what? Lithium's next, I believe. You got beryllium, boron, and so on. Now, within that, there are quantum numbers that correspond to the other angular stuff. And the first of those quantum numbers are L. The idea behind these L values is that they are less than or equal to n minus 1. So, for example, if n equals, say, 1, then L has a value of 0. So you just have hydrogen and helium. If n equals 2, then L can have values of 2. If n is 2, L can have values of 1, which would correspond to the second row there of the periodic table. And then the quantum numbers for the phi part of the wave function can be plus or minus values up to L. So that means you could have 0, plus or minus 1, and that would represent sort of your three values, 0, -1, and 1, which when you consider electron spin, which is basically the explanation for the p levels. So the s levels are like n equals 1, and then when you get to the p levels, it's like n equals 2, and these different angular momentum values correspond to the different orbital states. So you have a -1, a 0, and a 1. And then when you consider electron spin flips, you can have two electrons in one p level, two electrons, you have 6 overall. So this picture here illustrates what it would be like for, say, at a minimum, n equals 3. If n equals 3, then L can be 0, 1, or 2, and ML can be -2, -1, 0, 1, or 2. So this would correspond to, having 10 electrons in that level. That would be the next after S and P. You could have 10 electrons in that level. And that's what that corresponds to. So this is probably what you're more familiar with here. These are the quantum states. So where n equals 1, L can only be 0, and ML can only be 0, and that corresponds to the 1s level. Now, one thing that's not stated here is the electron spin. So you could put 2 electrons in this level. That's the 1s level. Then you have the 2s level, which is n equals 2, L is 0, and ML is 0. And that's the 2s level. For n equals 2, L can also be 1, which means ML values could be -1, 0, and 1, which is what the 2p level is on the periodic table. You go to n equals 3, that's the third row. You could have 2 atoms in the 3s level, and then L can be 0 or it can be 1. If L is 1, that's the 3p level, and you can have 6 different configurations there, and then below that, 10 configurations. Then we move on from there, we go to 4. You could have S, P, D, and then you get to F, and so on. So the entire organization of the periodic table ultimately arise from these 3 quantum numbers, N, L, and M sub L, and where the electrons go in these levels. So, it's kind of wild that the periodic table was developed like far before quantum mechanics, but then quantum mechanics comes around, solves a single atom, and then immediately we know why these quantum numbers exist. They correspond to the wave functions of all these atoms, and this is how we develop all these levels that you remember from chemistry. So it's kind of astonishing, but anyway, that's where these come from. Of course, the mathematics behind this stuff is kind of beyond us. We don't really have the tools to do that, so I'm not going to ask you to, at least for the hydrogen atom, to solve anything, because we can't do that. All the other examples were definitely things we could work with, All right, so I have some questions for you to see if you can follow that stuff. So do your best here. But, actually, this question here, I'm not going to have you respond to. I'm not going to have you respond to this because I'm going to rank things here. Rank the following states of the hydrogen atom from highest to lowest energy. Now, the energy of the hydrogen atom is dictated by only N. L and M do not dictate energy levels. Where L corresponds to S, P, D, or so. ML corresponds to how many electrons you could fit there, and then the MS is the electron spin. And the way it works here is you only look at N. So the highest energy is D, then A, B, C, because you're just going by the values for N here, nothing else. All right, let's do a couple examples here. Yes, we got a couple examples. So let's jump into those examples. Why is this up? No, it didn't be up. Where did I do with this example? I think I put it here. All right. How many distinct N, L, and M sub L states of the hydrogen atom are there with N equals 3? So if N equals 3, here's how we do this. If N equals 3, L can be 0, 1, or 2. Right? It's always from 0 up to N minus 1. So N equals 3, L is 0, 1, or 2. ML can be plus or minus up to L. So 0, plus or minus 1, plus or minus 2. That's always the principle here, is that N is always bigger than L, and ML can be equal to or less than L. So if L is 0, because everything is obviously N equals 3. That's set in stone. If L is 0, we have one state. Because if L is 0, ML has to be 0. And this is the S3 level. If L is 1, then you could have ML be 0, 1, or -1. There are 3 states. That corresponds to the S to the 3p level. 2 electrons here, 2 electrons here, 2 electrons here. Then we can go to L equals 2. So with L equals 2, M sub L can be 0, -1, +1, -2, +2. And there are 10 possible electron states here. Not thinking about electrons, though, there are 9 distinct states. You have the 3s level, you have 3 sp levels, and you have 5 3d levels. Now, because n equals 3, all the states are considered to be degenerate. They all have the exact same energy because the energy is only specified by the quantum number n. So that is 13.6 divided by 3. So every single energy state here is negative 1.51 eV. That's it. Now my next question here just jumps ahead and goes to 4. So it's the exact same problem, except when you have n equals 4, L can go up to 3, and ML can go up to plus or minus 3. So the same ideas apply, but now when we get into L equals 3, we can start getting into that F state where we have 1, 2, 3, 4, 5, 6, 7 distinct states, having 2 electrons in each state for spin up and spin down. Ultimately, you have 16 different states. All are the same energy. So it's given by the value of n, which is 4. So negative 0.85 EV is the energy of all of these states here. They all have the exact same state. All right, let's get back to this. So here are our probability functions for the different states in hydrogen. These are all given by probability versus distance here, basically. This is all distance divided by Bohr radius. So you can see that for L equals 0, all the different S states, S1 is very close to the nucleus, and 2 and 3 and 4 get further out. For L equals 1, the states look very similar down here. In fact, you've seen these before. If you've taken, any kind of chemistry, they've shown you these functions. This is what the 1s level looks like. The 2s level has this appearance to it where there's an electron in the center, one further out. There's 3 shells for the 3s level. And then you get to some of these really bizarre looking configurations where L can equal 1 or 2. And so you see all the different, now these are all orbital levels. These are all places where the electron can exist. Some cases they're spherically distributed. In some cases they have other kinds of symmetry. Very strange looking things, but these all come out of the wave function solution. So these orbital levels that you might have seen from chemistry, these all come out of these equations we've been working with here. So let's do one last example here. It turns out that the wave function for the very first level of hydrogen, so it's the only one I'm really going to show you here, is the wave function for the very first hydrogen atom is this thing right here. So 1 over radical pi a cubed, where a is the like Bohr radius here, e to the r over a. This is the simplest wave function for hydrogen. It's for, the electrons sitting in the ground level, the 1s levels right here. So let's look at that solution. All right, where is this? Right here. Oh, we want to first make sure that this is normalized. So that means we square the wave function, we integrate over all space, and we make sure the value is equal to 1. So when I do that here, I get 1 over pi a cubed. This becomes e to the minus 2r over a. And then the dv, I'm integrating over a sphere. So that dv turns into a 4 pi r squared dr here. And for this equation here, I can take out all the factors that are constant. That's going to give you a 4 over a cubed. And I'm going to integrate this thing here. Well, it's best to just look this up in an integral table, although I believe this is done with an integration by parts, but it's not a fun integration by parts. This is the integration by parts that will probably take you at least 40 minutes to do. So, of course, outside of math class, nobody actually integrates anything. That's just, I'm sorry, but if you go through a lot of math and you spend a lot of time integrating, the reality is that you don't integrate anything. You just look them up in tables.
I can confirm.
It's kind of sad, but it's funny because I have all these engineer friends in the area that I play, like, you know, I hang out with and stuff. And I always ask them, you know, like, oh, I teach this stuff, you know, what kind of things you want me to know? You know, do you care about the integrals? And they just laugh. And they're like, no, nobody knows any integrals. You have one or two things. The old timers have a book on their shelf, which is a table of integrals. And the younger folk go to Wolfram Alpha and they do their integrations. They said you cannot waste your time trying to integrate anything. It's just a waste of time, unfortunately. So sorry for all those who've been like kicking your butt. Yeah, but Wolfram Alpha is like, you future engineers, just buy the subscription and just go wild. I mean, it's like industry standard at this point, to be honest. Anyway, this integral, not the funnest thing in the world, but it does have this form right here. 3 different terms with an e to the minus r, 2r over a. And we're going to integrate this from 0 to infinity. Well, the infinity solution is not very interesting for us because that just goes to 1. The 0 is interesting, though. So anyway, infinity limits nothing. The first 2 terms here are 0 because of the 0 limit. And so you end up getting a 4 over a cubed and another a cubed over 4. Anyway, it all works out. Mathematics, to you know, for the win here. It's clearly normalized, so everything's good there. Now, the next step to this is to find a probability that the electron will be found at a distance less than a from the nucleus. Let me go back to my slide here just to be really clear about what we're talking about. Is this properly screen shared? Probably not. Whatever. What's the probability distribution here? Right here. Let's go to this. So here's our probability function here. So this purple line represents what's going on with the L equals 0 state. And so you can see here that what's the probability? Well, it looks like a good half of it is within just a few values of R here. It's kind of hard to see what that is. But what we're doing is we're integrating this between 0 and, I think, A here. So let's go back to that and see how that goes. Yeah, so we're going to take the same thing we did, take our wave function, square it. The dv becomes 4 pi r squared dr. We get the same, it's the same result, except we're not going from 0 to infinity, because 0 to infinity is 1. 0 to a is going to give us the probability that we are at least a distance 0 to a from the nucleus. So it's the same integral. We've got different limits here. So we plug in our values for a. We get some interesting things there. We get plug in 0, and again, the first 2 terms are 0. And you got to do a lot of algebra here, but we end up with the following expression. So this first part here is the a limit. The second part is the 0 limit here. This whole thing on the end becomes 1. And then we have a term over here, which turns out to be negative 5 e to the minus 2. And we evaluate that and we get 0.32. So what this is saying is that at the r equals a level, that's the Bohr radius, 1/3 of the time it's located within the Bohr radius to the nucleus, and 2/3 of the time it's located outside of that. And so that's what this is telling us, these wave functions here.